Thank you. Yes, you cannot hear me. Okay, now you can hear me. Can I? All right, thank you. Thank you. Good. All right. Any questions or any questions? You can tell me. Yeah, if you have a question, just let me know. All right. All right, let's start, okay? Right. So again, for a midterm, we're gonna go up to our coordinate maps. We will talk about inverse and coordinate maps, and that will be the stop, the cutoff. And then this diagram change of basis gets pushed to midterm 2. Okay, well, I will tell you when the cutoff is, like on the slide. Like I will tell you, we stop here. I should have written cutoff. I will write it later. But okay. Questions? All right. Right. So to talk about inverse and compositions, we need to talk about the space of linear maps. So we've talked about vector spaces. We've talked about linear maps. Now we're going to talk about the vector space of linear maps of vector spaces. Okay. So you should think about this as the this is inside functions from V to W, right? So if you remember, we had these functions, right? V to W, and the simplest case was functions R to R. So, just graphs, but they can be non-linear, like exponential. So we're going to look at all linear maps, all right, between those two vector spaces, V and W, and they have to have the same field. So I know we never say that, but we always assume that V and W have the same field. Otherwise, scalar multiplication makes no sense. All right. So yeah, A is in F, which is FV, which is FW. Okay. Just to make sure. And we're not just doing reals, we're going to do everything. The entire field, complex, finite fields. Okay. All right. Is a vector spaced. So a quick way to check vector space is you just need closure because we've already done that. This guy here is a vector space. So you just have to show the subspace criterion, and yeah, so you just have to show that A T plus S is inside linear maps of V from W. And I think that's clear, right? If T and S are in LVW, right? Because you just do it pointwise. So you just do it pointwise because, what should I say? Because ATV plus SV is in W for all V in V. Because W is a vector space. So you can add the images. Okay. So that's all. Well, you just had to check the subspace criterion. All right. So that's what we're working on. We're working on the space of linear maps. And we're going to talk about multiplicative inverse and now the composition. So I talked about a little bit about composition. So just to remind you, I might as well go there. So where is it? Whatever. I'll just do it again. Anyway, so yeah, we have three vector spaces. So we go from T goes from V to W, and S goes from U to V, and R goes from Z to U. So then you can compose them. So R, S, and T. So this guy goes from Z to U, which goes to V, and this guy goes to W. Right? So there's nothing new here. Like everything you've seen in calculus, everything is the same, how compositions work. So for example, let me ask you a question. I mean, it's kind of stupid. Is this true? Can you swap compositions? Do you guys have an example here or in the chat, in spirit? Can you give me two examples of, because like there are cases, right? So, like linear maps, right? So take something like S to be AX and T to be BX. These are, you can swap them, right? So they both equal to ABX. But what's an example where it fails? Anybody? No? I mean, it's easy actually. Like you take S to be the constant function and take T to be the exponential. Then ST is still 2 because it's the constant function. It doesn't matter what you put in. And this guy is the is equal to e to the 2. Again, a constant function, but a different constant function. It's like the stupidest example. All right, so you do not have commutativity for composition. So no commutativity. That's why you cannot have a vector space built on composition. Because you need this basic axiom. So in the book, they go over these axioms, but the one that's missing is commutativity. So you can compose S and R and then compose with T, or you can compose T with S and then compose with R. So it's the same business. Oh yeah, they give me some X plus 1 and X squared. Actually, let me try it. I'm sure you're right. So X plus 1 and X squared. One gives you X plus 1 squared, and the other one gives you X squared plus 1. Yes. And they're not the same. Good. Thank you. Right. And you prove all these things pointwise. But okay. Yeah, so distributivity, same thing, you do it pointwise, and what should we explain? Yeah, so from here to here is just the definition of composition. And from here to here, you use linearity of T. Anyhow, I mean, we're not gonna test you on this thing. So it's not really, it's mostly for your understanding. We're not gonna ask you go axiom by axiom. For these are just for you to understand what's true. So also, yeah, here, that's the final thing. So for identity of V, we just mean send V to V. And identity of W, we mean send W to W. So again, you do not have a multiplicative identity. So when V is not W, IV is not IW. So if you remember from fields or whatever, you had the multiplicative identity, right? Like you had like 1 star X was equal to X star 1 or whatever. So here you don't have that because the vector spaces could be different. But if they're the same, you do. But you still don't have commutativity. Okay. All right. So yeah, you're missing commutativity. Any other axiom we were missing? What do you think? From vector spaces or fields? Yes. Right. So we don't have an inverse. And when do we have an inverse? Do you know by chance? Like when is a map invertible? Oh, so you wait, are you talking about? No. But that's wait. So you're just talking about surjective. No, like the problem happens when you send 2 guys to 1, because then how do you define the inverse? You cannot split the image. So what is that called? What do you need to have inverse? No, you just need injective. So you could still have this, like like e to the x, right? It goes from r to r plus, and its inverse is log of x from r plus to r. So it doesn't, like, this is within r. I mean, it's not. Do you know what I mean? Like, so it doesn't have to be. It has to be bijective in its image, which just means be injective, because you're always surjective in your image because it's your image. Is that okay? So you just did injective. So no inverse. No inverse because we need injective. Is that okay? What exactly are the identity maps? Oh, there's more questions. Shit. Yes. No, you just need one-to-one. The identity maps. What are the identity maps? Oh, yeah. You take a V and it gives you back V. You take a W and it gives you back W. Next. Is that okay? All right, you can tell me if it's okay. All right, fine. So you do not have a vector space of compositions. You don't have multiplicative inverse, additive inverse, all that stuff. No, actually, you do have additive inverse. Multiplicative, you don't. All right. This is in your book. So all it says is something very obvious. So if you have a map S and has a kernel of S, it maps it to some to 0. So yeah, and then you have another map T. So this is S and this is T, and it has its own kernel. So it goes like this. It says that if you look at the kernel of the composition, it contains the kernel of S. Now let me ask you a question. So why isn't it kernel of S equal to kernel of TS? What could possibly happen that you could have more elements that give you 0 for T of S, what do you think will happen? Oh, yeah, sir, yeah. Perfect. So take some element outside the kernel of S, call it V, and it sends it in here, call it S of V. And S of V is in the kernel of T. So then you have T of S of V, call it Tx, would be 0. Is that okay? So V is not in the kernel of S, but it is, its image is in the kernel of T. So then together, they're 0. S of V is not 0, so S of V is not 0. Does that make sense? Isn't it supposed to be kernel of ST instead of? So, I mean, what? No. So what happens, right? This is the U, this is V, and this is W. So S takes U to V, and then T takes V to W. Yeah, is that okay, Ismail? Okay, I don't know. You don't need them to be equal, and they both have the same kernel. No, the kernel is always in the domain, right? So kernel of S and kernel of TS are both inside U. Okay. I mean, we can talk about this more. All right. Okay, so yeah, you take, so the first one is easy. You just take a V in the kernel of S. So S of V is the 0 in V. So then when you take both sides of T, you get 0 of W. So yes, kernel of S is inside the kernel of TS. All right. So this is not in your book, so you're not going to be tested on it. But I wanted to give you this, just if you want to do some practice problems or you have some questions, you know, this is a quick way to check your understanding, right? So these are results that we're not going to do in class, but you can use them in your draft work. Does that make sense? So if you know that, so this is the general statement that the kernel of T of S is always less or equal than the kernel of S plus kernel of T, which we just said that this is bigger than dimension of kernel of S. So you have a two-sided inequality for the dimension of the composition. Is that okay? Yeah. I guess I want to ask you, that's all right. Since we're not going to be tested on it, doesn't matter. But when you have the exact same spaces, then you have this split. So the two kernels give you the whole thing. Okay. So anyways, I mean, we're not going to do this, but you can use it. So because the book only gives you the partial picture, the lower bound, but more is known. No, yes. No, it doesn't have to be. Yeah. I just forget sometimes. Yeah, same thing here. Because they could both be identity maps. So you always have equal. Yeah, thank you. All right. Why did we need surjective? Right. Anyways, you're not going to be tested, so we don't have to go too deep. But yeah, if you take S to be 1, then what's the dimension of its kernel? Any ideas? Zero. It's never zero. But is that okay? So it just says that you can take t to be anything, like take t to be like a polynomial, or no, what do I want? What's a nice kernel? Like the projection map. So dimension of the kernel of the projection from R2 to R is 1. So you have 1. And here you have 0. And this is, I want to say this is also 0, because P of A of 1 is always, I mean, it doesn't even make sense. So I should say something like, maybe like, so project to 1, 0, and take this to be 0, 1. So then 0 of 1 is always 0. So yeah, so you get 0, 1, 0. Anyways, there's a lot of games you can play here. Okay, questions? No questions. Well, let's do some stuff that you will see. So this is in your book as well, but I do it for general values. So in your book, they do this for A equal to 1, 0. I mean, U naught. And theta equal to pi over 4. And what is that? So the first guy says project. So give me the span of U0. So this is the span of U0. And then if you give me any other vector, this guy here is called the projection. So call this, I call it V. So this is PU0 of V. That's what we mean by projection. Okay. And rotation takes the V and moves it by angle theta. So this is rho theta of V. Just turns it around. So then the question is, yeah, how does the composition work for these two? So you first rotate and then you project. So we're gonna check all our theorems for dimensions. All right. So yeah, let me ask you some questions. So what do you think is the kernel, the dimension of the kernel of rho theta? So you guys can tell me here in the chat the number. Is it 0? Is it 1? Is it 2? What is it? One. So you're saying that, yeah, people don't. So, right. So let's see. Pictorially. Pictorial is the best way to see this. So 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 if you mean some vector along the axis or what? Yeah. Okay. So what's the dimension then? Right. So right. Yes. Perfect. Yeah. So yes. I mean, and you can. All right. Anyhow. So yes, the dimension of the 0 guy, just the 0 element. So let me explain why is it only that. So pictorially, it's easy. You know, if you give me any vector AB, obviously I will move it by some angle theta, as long as it's not the 0 vector, because the 0 vector gets trapped. I mean, you can just, you know, you have your matrix cosine 0, 0 gets mapped to 0, 0. It didn't get rotated. But okay, what's another quick way to see this? Actually, I will do this later with the inverse, but I will show you how to invert this matrix. So there's another way to see it, namely that, remember, kernel of R theta are all the V's such that R theta of V is 0, 0. And you can show easily later that R theta is invertible. So you get that V is R theta inverse of 0, 0, and we'll show that this is R minus theta. So the inverse of moving by theta is the same as moving by minus theta, the other way. And this will give you the zero vector. Is that okay? So yeah, we will talk about all that stuff. Any questions? -1, 1. No, it's just the zero vector. Okay. All right. For projection, I think is easy. But I should do it regardless. Kernel of projection. So, yeah, any guesses? What's the, is it 2? Is it 1? Is it 0? What's the dimension of the kernel? Yeah. What is it? Why 0? Yeah, I even good. And then, right. So, but then the question is, what's the dimension of that space? Yeah, so let's see it again. U0 of V equal to 0. That's the kernel space. Okay. But we define this. This is the U0 dot product with V normalized U squared times U0. Okay. You kill off this guy over here. So you're left with UV, and U naught was AB. And in AB are, what do I want to say? Anyhow, so yeah, AB is, this should be 0, 0. You have U0VA is 0 and U0VB is 0, but we take the thing you projected to be non-zero. So it's not the origin. So at least A or B are not 0, which force the dot product to be 0. And when do you have a dot product being 0? When the vectors are what? You can yell it out. Huh? Yeah, it's just when they're orthogonal. So you have your U naught crossing the origin, and then it would just be this line over here. That's it. So you take all these V's, and this is a line, and it even has specific coordinates. It's A minus B. When, you know, where U naught is AB, because the dot product is 0. So you take any scalar multiple of A minus B. So it's the span of these guys. Is that okay? Does that make sense? Yeah, you can ask. Is that okay? All right. So let's go slower. I think, okay, you can tell me. Let me see. So yeah, let me write it out. So the kernel of P0AB are all the V's, so that U naught V is the origin. And then this is just the span of A minus B, which is one dimension. All right. Moving on. So the answer is 1. Oops. Right. Yeah, so then, right, so let's do this just for practice. So then what's the dimension of the image of U naught? What's a quick way to find it without any pictures? Just how does the rank nullity gives us the answer? Yeah, go ahead. So then, like, what should I write here? Uh, right, yeah. That's all. I just want to see that, yeah. So you have 2 minus 1, so it's 1. Yeah. Good. Anyhow, we talked about this rotation. Yeah, I'm gonna come back to rotation matrix at the inverse. So let's leave it for now. Right. So then, so yeah, let's see. Dimension of projection, rotation, but for the kernel. So yeah, any ideas? What's the dimension of the composition when you first rotate and then you send it down to U0? Is it, you guys can say in the chat too, is it 0, 1, 2? What is it? What do you think? Why? Yeah, exactly. So let's see, how will we, is that what people said? Why is it not two-dimensional? I don't know what. Are you talking about the main map? Are you talking about the projection of the image? Oh, I see. Well, I mean, okay, so this is what rank nullity gave us, but why is it true that it's one-dimensional? You can see it from the formula. So PU0 of V is some constant times U0. Like, so it's always, some multiple of one vector. Is that okay? Like C is just a number, this dot product, whatever, it's a number. And it's times the vector. So it's always 1D. Is that okay, Meima? Okay, now you mean the kernel. What is going on? The kernel. Oh, why the kernel is not two-dimensional? Oh, because you could be in the, you could already, what's the definition of kernel? It's all the V's, so that 2U0 V is 0, like the origin. And we just talked about that. This is all the, it's all the vectors that are dotted to be 0. And we found the span. So we found this exactly, that it's 1D. Okay, we can talk about this more at the end. Let's come back to it at the end. All right. So yeah, right. So dimension of composition for the kernel is still 1. So what's a way to see it? So you have PU0 rho theta. What is it? Some, I don't know, CD gets mapped to 0, 0. And so we're asking, right, but we already computed it. So kernel of R theta was just the 0 vector. And moreover, what else? What should I say? So let me think. Right, so we are talking about image of rho theta. and that is all of R2. So that's the reason. So, okay, let me explain. So you have dimension of kernel of rho theta plus dimension of image of rho theta is equal to 2 by rank nullity. This guy is 0, and this guy now is 2 then. So you can get from the result we proved before that that implies that image of rho theta is the entire space. So nothing changed. So P of U0 acts on R2 as if it's just R2. You didn't go to a subspace of R2. You have the full space. Is that okay? I mean, for us, if you write this, is okay, but it's for you. If you can let me know. Okay. So that's all. It didn't change. You have the same domain. You just move things around. Right? Okay, let me write it out a little if you're still confused. So this tells us that rho theta is surjective. Okay. So that means that rho theta CD is some vector W for any W in R2. So that means that PU0W acts on an arbitrary W. So and then if you ask for W to be in the kernel of PU0, you can always invert all these arrows. So that would mean that you give me any guy from the kernel, I can generate it from another vector CD. Or I don't know, okay. I can go in more detail, but if you write this stuff, it's good. Okay. I can explain more if you want. Why is dimension kernel of okay, we can talk about this more at the end. So, all right, let's start with the inverse. So yeah, as someone mentioned before, so yeah, so right. So you have some function from V to W, and by inverse, we just mean you take the element here, you map it here, and you can map it back by some function G, and we want it to go both ways. So we're not just asking for G of F to be X, we're asking for also F of G to be X, or to be Y, whatever I say here. So we want two-sided inverse, because there are maps where you have it only one way. Yeah, I have like, anyways, but they're too complicated. It's not worth it. All right. And finally, let's introduce our main object for the rest of the course, called an isomorphism. So whenever you can invert your map T, we call T to be an isomorphism, and we call these two spaces isomorphic, and we write this notation here. Okay. So whenever this is possible, and it's not always possible. For example, remember we talked about that V is W. I mean, this is different here. I'm not saying isomorphic, I'm saying equal. We said that this is true when their dimensions are equal. And the same thing will happen here. You only have an isomorphism when the dimensions are equal. So we proved this before, recall. We can extend the same result here. which is kind of crazy because they don't even have to be the same things, as you will see. Okay, any questions? All right. Yes. Oh yeah, we're gonna prove this. That's the beautiful part. It's called coordinate maps. So we're gonna show that they're perfect, that there's a canonical map. So if you have the dimensions are, thank you. So this is usually given, some given t. Let me write bigger. So this is usually you have some given t isomorphic, right? Like invertible. And this is, it gives you the dimension, but then you can also build an isomorphism. Yeah. If you know that what? Right, right. Yeah, it's not obvious, but it's always possible. There's a canonical way. Yeah, okay. All right. Yeah, I mean, that's the amazing stuff. And yeah, okay, we'll talk about this. Yeah, let's do some examples just to get some practice. So can somebody tell me here or in the chat, what's the inverse of t of x? So what will give you x? Yeah, so what is t of y? Any ideas? Yeah. Good. So if you just, so if a is 0, so let's start with the easy one. If t of x is the 0 map, what is its inverse? Huh? I know, we're just playing with the, I just want to make sure you're all okay. So what will be the inverse of the 0 map? Yeah, yeah, yeah. Wait, can you do it? Oh. Let me see. As you have scalar multiplication, right. Then you're not injective. Okay, thank you. I don't know what I was thinking. Thank you. Yes. So if it's identically 0, then you're not injective. So then you're not invertible. Okay, thank you. But yeah, here you just take 1 over y of y. So then t inverse of t of x is equal to 1 over ax, which gives you x. Questions? 0. No, it's not like this. Will said, it's not injective. Yeah. All right. Yeah. So geometrically, what's the inverse of the rotation matrix? I sort of alluded it. So you gave me some v. I rotate by theta. So if I want to come back from, call this guy w now, I have to move by minus theta. So r minus theta w. So geometrically, that's the inverse, but we're not a geometric course, we're an algebra course, so we have to prove stuff. So let's prove some stuff. So yeah, the claim is that the transpose of your matrix is in fact the your inverse. So we're claiming the claim R transpose of theta is R inverse of theta, and this guy here will be R minus theta. So we have this chain of equalities. So first, let me do the first step for you here. Let me get you the 1. So how do you get the top coefficient? You have cosine theta times cosine theta, and then sine theta times sine theta. Right? So you have cos squared, sine squared, which is 1. Okay, and for the other ones, you have cross terms. Okay, so we have the inverse, so that's checked. Okay, now the question is, why do you get r of minus theta? Okay, is that okay with everybody? All right. All right. So what is r of minus theta? You have cosine of minus theta, sine of minus theta, and what else? Minus sine of minus theta, and cosine of minus theta. All right. What do we know about cosine of minus theta? Here or in the chat, what is it equal to? And it is? Is it self what? Yeah, it's exactly, yeah. So it's cosine theta. Sine theta, you pick up a minus. So this is indeed just the r theta transpose, which was the inverse of theta. All right. So they go over this in the book as well, if you want to see it there. But they don't include the proofs. I'll give you the proofs. All right. Yeah, does the projection map have an inverse? What's a quick answer? And can somebody tell me why not? Thank you, Mayma. Yes, I should have checked them. Can somebody tell me why here or in the chat, why we don't have an inverse for the projection? What's the quick answer? Sure, yeah. Yeah, so dimension of kernel of PAB is always the dimension of the ones that are orthogonal to it, which is always a dimension 1. So you always have a one-dimensional object is always 1, so it's not injective, and you need injectivity. Why? Because if you map two things to 1, then you cannot invert that. You cannot decide where do I map to. So it's not a well-defined map. All right. I mean, we can approve this. I'm just, we can approve why you need injective. Not 1-to-1, yes. All right. Okay, so as promised, yesterday we talked about that the dimension of n and n is equal to n squared. And I learned from this from CS, actually, computer science. So this shows up when you want to make a matrix array into a vector, right? So this is called row ordering map. You don't want to see it in math. It's not even in our textbook. But I thought it was cool because like you need some canonical way to figure out the dimension. I mean, you can do it with the basis vectors and do a counting argument to get n squared, but I want to give you the map. So let me explain this map. So how does it work? Let's do it. Which one is easier? Yeah, let me do it the easier way. So yeah, let me start with the matrix. So you give me some matrix, Aij, then you want to map it to some n square vector, right? And you're going to map the entry Aij to xk, where you set k to be n I minus 1 plus j. Okay. The reason this works is because it works the other way. So, so if you start with an xk in 1n squared, you do Euclidean division, and it gives you some with respect to n. So you have n multiple I minus 1 and then a remainder j. Okay, so pictorially, you're just going like this. If you want to, you can play around with it, but that's what you're doing. You're going this, and then you're going up, and then you're going down, and then you're going up. You can play with that stuff. So this is the map. Okay. When it comes to matrix M n by n, I thought of dimension be described as degrees of freedom. Yeah, because it's the number of, right. So in R3, you have 3 ways to move. And we're gonna prove this, that dimension of V equal to n implies that V is isomorphic to Rn. So all your intuitions for Rn carry through to vector spaces. Everything, the degrees of freedom, the basis, all that stuff. So same thing. Oh, okay. All right. Thank you. Yes. Yeah, thank you. Yes. Yeah, yeah.
One of our questions is the union of two bases of two vectors XPF is the spanning set of U plus W.
Right, 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 right.
The way I interpreted it, it's with proof set equality, right?
Is by what?
With the proof set equality, the span of U union W is a subset of U plus W, and then U plus W is a subset.
Right. So what do you want? Let's go outside because I'm getting kicked out.
How's it being back?
Yeah.
Which class is this?
Linear
Sorry?
algebra.
Linear algebra. No idea what that is, but it looks really cool.
Sometimes they bore you.
Huh?